Welcome all, this is Saud, and welcome to video part 2 of microprocessor principles and architecture. If you didn't watch yet video part 1, I recommend you to do that before proceeding with this video. You can get the link to video part 1 at the link in the description of this video. At part 1, we went through brief of these processors and microcontrollers. Then simulation of microprocessor external bus. In this video, we will zoom in to see inside the CPU. This processor architecture belongs to very early and older microprocessor technology, that is Intel 8085. When we move to newer processor, that is Pentium 4, we clearly notice the amount of complexity added to microprocessor circuitry during the years. Newer processors started implementing number of techniques to improve performance. Example of that, pipeline and branch predictions, using cache memory, implementing higher clock speed, plus introducing multi-core CPUs. Also implementing hyper-threading technology. And to further boost the performance at system level, parallel processing computer organization was introduced. Pipeline concept is a technique where multiple instructions are overlapped during execution. So pipeline is divided into stages, and these stages are connected with one another. Therefore, when instruction number 1 move from fetch to decode, at same time instruction 2 move to fetch stage, then the time instruction 1 move to execute stage, instruction 2 move to decode stage, while instruction 3 at that moment enter the pipeline for fetch stage, and so on. Very fast, let's go through few of these blocks. The processor connects to outside world through the bus interface unit. The concept of cache memory is very important. The external dynamic RAM is running at far lower speed than the internal microprocessor logic circuit and clock. So if the CPU try to fetch the instruction every time from external dynamic RAM, that will slow down and drop microprocessor performance a lot. Therefore, cache memory is loaded with frequently used instructions and keeps the instructions ready to be delivered to CPU front-end stage at higher speed. This provides almost immediate access to data with minimum delay. Cache memory is static RAM type, which is much faster but expensive compared to external dynamic RAM. Another good fact in this architecture, the already decoded instructions or micro operations from the decoders will be all stored at write sequence in the trace cache. This is considered as level 1 instruction cache. The micro operations will be executed now from the trace cache sequentially. This step, of course, boosts the performance of decoding process, eliminates the bottleneck of needing the instruction to be decoded one by one every time. The interesting thing about decoding instructions, the zeros and ones of the instruction opcode itself represent unique control signal per every instruction opcode, that is having different bits patterns. So after decoding the opcode content, these signals directly drive the combinational logic, which is triggered by the clock signal with repetitive sequence of pulses from the internal timing generator to produce all the control signals. Among the problems affecting pipeline process is the presence of branch at instruction execution and jumping to another instruction address during implementation of a program, and that would hinder the flow of instructions. Therefore, here we have accurate branch prediction logic that uses the past history of program execution to speculate where the program is going to branch to help preventing frequent flashing the pipeline. Some processors use a simple static branching prediction technique, and some they use dynamic branch prediction based on branch history analysis, and that is the case here. The trace cache generate decoded micro instructions in order of first in, first out, going to the out of order execution logic section. But this is for simple instructions only. In case of more complex instructions, which normally decoded to more number of micro instructions, the trace cache gets support from microcode ROM, which is a memory storing for micro instruction program. These, we can say, are defined digital words for every instruction to drive the control signals. Here we have what's called out of order execution engine, is where the instructions are prepared for execution. This part of machine will reorder instructions differently to allow them to execute as quickly as their input operands are ready. The out of order execution logic has several buffers that is used to smooth and reorder the flow of instructions to optimize performance as they go down the pipeline and get scheduled for execution. Later, the instructions will be brought back to the original program order after they complete execution. At this area, we have the heart of CPU, which is the execution unit, where the actual work is performed, and here the instructions are actually executed to obtain the final computational results. The execution unit include several types of integers arithmetic logic unit and floating point execution with MMX unit to speed up multimedia applications execution, and all produce the final results. At this point, also we have the level 1 data cache that is used for frequent load and store operations. Special thanks to microprocessor inventors for the great effort to build out microprocessor at very early stage. And also great thanks to microprocessor developers. They really doing a great work and effort to deal and design such complex systems which is serving humanity. The truth is, I'm not a microprocessor expert at all. I just like to learn and study microprocessor. And here I am providing some thoughts and suggestions towards slightly different microprocessor architecture, thinking of future demands for more machine learning and computing power. I'm presenting this, it's my own idea with suggested design, hoping this will inspire for more innovative ideas for further microprocessor developments. The main idea is to minimize obstructive processing and get the instructions just flow smoothly through minimum steps. The architecture is based on fetch execute instruction cycle instead of fetch decode execute. So one bottleneck of decoding stage is eliminated, plus some other self-learning ideas will be explained as well. The instruction consists of control word and operand instead of opcode and operand. And in fact, the idea presented as high-level system description, but implementation detail will be left to the designer and system developer, depending on the available technology. The suggested architecture is built of dynamic logic units, and the control word selects and enable directly the execution hardware unit to customized property for every instruction. So no any need for the opcode to be further decoded. It's just the data to be processed through the selected logic. So in this architecture, the execution logic circuit is not a common circuit driven by the micro instructions code to perform different operations, but instead of that, every operation is executed by a dedicated logic circuit selected directly by the control word passing through the logic switching manager. The arithmetic and control unit consist of sub-arithmetic units to deal with every particular operation selected by control word independently. Another point, in this architecture, we have two internal data bus to move at least two data operands simultaneously. Therefore, at fetching stage, the data will be immediately loaded and flow on the internal bus as the data is proceeding the control word at instruction level. And microprocessor selected execution subunit will be directly enabled and connected to deal with the operand and perform required operation with minimum clock cycles. So for example, to add two immediate values, the value 1 will be loaded on data bus 1 and value 2 on bus 2. The control word will switch and select the sub-ALU logic part, which was defined to handle two values addition and write back results. And because two data buses are used, then there is no need to store one of the values in temporary register before performing the operation as usual. But instead, both values will be available at the input together. Same concept for compare operation. The execution unit enable and connect the appropriate logic circuit for comparing the operands. which will perform the operation and set the flags accordingly. If the operand is address, in case of direct addressing mode, for example, then the memory address register will be set by logic switching manager to accept the address, which will be already available on the bus and loaded to the external address bus for normal memory location read, and so on. Yes, this may lead to extra hardware complexity, but I am also sure this still can be achievable with nowadays advanced silicon fabrication technology. But then we will need to achieve further reduced instruction set computer architecture with even a smaller number and breakdown of instructions to minimize hardware size. So with this architecture, we will end up with general purpose processor which has got the capability to be further customized for specific applications, which in turn will gain additional performance boost and deliver maximum computational workload. Then we can also produce specific breakdown versions of this processor equipped with only required selected sub ALUs to fulfill certain application to achieve more gain in performance. And what can bring the processing capability to totally different level is to develop the execution units in a way that they learn the program objectives. So instead of having the processor just dummy instruction execution device, we end up with a microprocessor that interacts with sort of consciousness to the running applications and software. In fact, we already do sort of that through dynamic branch prediction. Why not to bring this concept down to the execution units and develop enough sophisticated prediction intelligence to directly execute some of final results at defined conditions without even fetching instructions. And that can be achieved in number of ways. One direction, and this will work well with repeated instructions, is to provide a mechanism for the execution unit to save copy of most recent executed results at special cache. We can call it execute operation archive. Then provide continuous feedback from the front-end fetching unit to the execute prediction unit with enough details of current fetched instruction. The execute prediction unit keeps a track of every recent executed instruction, and it will know if the same instruction was already executed and which copy of final result at execute operation archive to be used, and based on this it will just execute the same result directly without needing to process that instruction through. Then discard the current fetched instruction and allow increment of program counter to load and fetch new instruction immediately. Also, the logic switching manager keeps tracking what is the most executed operation all the time. So it sets and switches the sub-execution logic in advance to that particular logic mode immediately after completion of every execution. And when new instruction is loaded, and if the same control word is requested, then it will just allow the operand and data to directly pass for execution, because the right logic mode is already set and connected. Therefore, just go ahead and process the data, and at the same time discard the current loaded instruction and fetch the next instruction immediately. In this architecture, I suggested to have internal integrated CPU, learning engine CPU. This CPU doesn't need to run at very high speed, and it doesn't need to interact or obstruct the main internal microprocessor bus at all. It works alone at the side, and through interrupt request, it will steer the execution. This can play very good role in terms to learn what's the main program trying to achieve. Then it can further adjust the execution to closely deal with the other changing conditions which are not in consideration of main program. This feature will be so useful, especially with robotic and auto driving applications plus control system implementations in general. The learning engine CPU will be loaded with a firmware program of computational thinking algorithms and machine learning intelligence. And this CPU knows and tracks the fetched instructions, also the final execution results and history. It can request to read from external address at any time through interrupt control. And based on computational outcome, it can write new instructions to be executed or pick up and write final results from archive to improve execution. The important tool here, the compiler, should be designed to generate basic decision-making inputs for this CPU while compiling the main program. And same option can be given to the programmer himself. Then this can be loaded to the CPU as supporting file. Last thing, I am suggesting to add digital signal processing DSP unit to be one element of execution unit as well, beside current ALUs. That's all, and thanks.